covers Griffiths E&M section 5.3, example 5.8. We've previously done a problem where we talked about the use of Ampere's law to calculate the magnetic field when you have a nice symmetry to exploit. That says that B dot dl is equal to mu naught I enclosed. Okay. You pick a particular path, you integrate the magnetic field along that path, and that is equal to all of the current that crosses through the area enclosed by that path. Just like Gauss's law, there are other kinds of symmetries. So the circular loop that we chose previously is not the only kind of Amperian loop we can draw. Let's go ahead and imagine that we have Cartesian symmetry. So this is X, Y, and Z. And we have a sheet, an infinite sheet that has a surface current density K, which is some magnitude in the x-hat direction. Okay, so let's see if we can draw that. Something that looks like this. And it lives in the xy plane. And the current flows in the positive x direction. So it's in the xy plane. All right. So it's always good to kind of figure out which direction or what shape and what orientation your loop should be. And I think the natural question here is, which direction is the magnetic field going to point? Or alternatively, which direction is it not going to point? I think we can make the argument fairly, without too much struggle, that the magnetic field is not going to be pointed in the x direction, because the magnetic field always, because of the cross product, is perpendicular to the current, and the current is in the x direction. Okay, so that leaves us with y or z. Okay, so let's go ahead and draw a side view of this. Here is the y-axis. Here is the z-axis up, and I have a whole bunch of current using our sort of arrow notation. It's all coming out at me. I'm drawing it as discrete lines, but you know this is a continuous charge density or current density. Okay. So I'm going to make the argument that we should go ahead and, since we know it's not in the x-hat direction, we can pick a path that travels along the z and y directions, and then we're going to further make an argument that one of those is not particularly relevant for us. Okay, so I'm going to pick a loop. It's going to be a rectangle that is in the zy plane. I'm going to go ahead and travel. Let's go ahead. We're going to say we're going to travel this direction. Okay. And now, so this is our Amperian loop, and now our job is to go ahead and calculate both sides of this Ampere's law. Okay, so if I'm going to go ahead and calculate the left side, I know that I need to do 4 integrals. Right. The reason I need to do 4 integrals is because dl is changing as I go along each of these paths. Okay. dl is in the z direction for 2 of these, and it's in the y direction for the other 2. Okay. So I need to go ahead and take this integral over 4 paths. So I'll do 1, 2, 3, and 4. So the total closed path is equal to b along 1 plus b along 2 plus 3 plus 4. Okay, now I'm going to make the argument here, though, that if I were to, let's extend this infinitely long, or closer to infinitely long. If I were to pick, let's say, this point, this bit of current, which direction does that magnetic field point at? Let's go ahead and pick a simple spot at along the y-axis at the loop that we've drawn. All right, I know that this current, since I'm looking at it from a particular direction, is going to generate a magnetic field that looks like a loop. I use the right-hand rule. Maybe I shouldn't use an X here, but the current is coming out of the page. Right-hand rule says that the magnetic field is then going to be pointed up. Okay, if I look the same distance away to the right, I get the same magnitude of the magnetic field at my loop, but it is now pointed down. So because our sheet is very big, there's always going to be a contribution to the magnetic field from the left and the right that's going to cancel out every element along here. So these two paths are 0. Okay, so now we only have 2 integrals to do. All right, I have chosen this loop to be the same distance away from the top and the bottom, from the y-axis. Okay. Now we need to go ahead and calculate the integral of b bottom dy plus the integral of b top dy. Okay. And you'll notice that we're going around different directions, right? I'm going to the right on the bottom one, I'm going to the left on the top one. And although I'm going in different directions, the magnetic field at each of these regions is pointed in different directions. So at the top, the magnetic field is pointed to the left, and I'm traveling along that. So that dot product is something that's positive, and the bottom, the dot product is something that's also positive. Right? They're both pointed in the same direction. Okay, so that's what I've kind of been cavalier about these vectors. And because I am because I have these lines at the same distance away from this plane, these are both the same magnetic field, same magnitude. All right. And we're going to make the argument that this magnetic field is constant along this path, so I can pull it out. And this loop has the same length on each direction. There we go. All right, each to the top and the bottom lengths of this loop is with L. So I'm left with 2BL. All right, so that's the left side of Ampere's law. The right side of Ampere's law is mu naught I enclosed. What is mu naught I enclosed here? Well, it's just mu naught times the current density, K, times the length perpendicular, which is L. I have this much current going through that surface. All right. Therefore, 2BL is equal to mu naught KL, and B is equal to mu naught K over 2. Oh, interesting, it's constant. Okay. Now I have to add the direction afterwards, right? That was the rule for Gauss's law, and that's the rule for Ampere's law previously, is that you have to add this direction post hoc. But the direction is going to be different depending on which part of my integral I am doing. Right? So it's not such an easy or such a clean result in the end. But I'm left with saying that the magnetic field is now equal to the same magnitude, k over 2, but I have to specify in which region of space it's positive and which region of space it's negative. Okay, so above the xy plane, right-hand rule tells me it's pointed to the left. And above and below the xy plane, the right-hand rule tells me it's pointed to the right. That's our full result.